Okay, so we're going to do part 2, in which I talk a little bit about forces, different types of forces, and getting into some drawing of vector diagrams in order to solve for Newton's second law, which is the law of acceleration. So looking at F net equals to ma. So that is what we will do briefly before my next class. So types of forces that we talked about. Alright, let's see if I can get this better focused. Okay, that looks a little bit better. Okay, so types of forces. We had, I think our first one that we looked at was Fg, and we call Fg gravity force or weight force. Remember that gravity is not 9.8 meters per second squared, but that the acceleration due to the force of gravity on Earth is 9.8 meters per second squared, or what we've been using, 10, right? You can use that on the test, that's fine. Okay, so these are different. Gravity is different based on mass of the object and the closeness to the center of the Earth's mass, right? So up on a mountain, you would have technically marginally less weight than you would at the Dead Sea, for example, because of the sea level, or in New Orleans. So the gravitational attraction between you and Earth depends on how much mass you have. So you are technically more attracted to Earth potentially than ever because you were born with way less mass than you are now, and so you are way more attracted to the Earth now. So gravity is not that, but the acceleration caused by that attraction is a particular number on Earth, and we keep that as a constant. Okay? We also learned about what we call FAP, right? We say, applied force. And that's, here's a box, I apply a force to try to move it. That could be a pull or push, right? So it's any type of application of a force. And we just label it as FAP. We also have F parallel. Which, if an applied force is applied parallel, you could label that as an F parallel. We also have F perpendicular. And we use these a lot when we talk about angles and labeling things. We have the normal force, F nor or Fn. And the normal force acts perpendicular to the surface, right? So if I have Fg, F normal is going to act up against that at a right angle to that surface, and at this point they are equal, right? If it's these two forces are going to be equal. When they're not equal, if the object is on a slant, right, gravity still is drawn down, and the normal force is still drawn up at a right angle. And in this case, these two forces are no longer equal. Okay, the normal force will be less than the weight. Okay, it's always going to be equal to, if it's on a flat surface, or less than the weight force. There's only two options. So that's our normal force, so it always acts perpendicular to the surface, and only when it's on a horizontal plane are gravity and the normal force actually equal to each other. We also learned about static friction. So we have Fs, so static friction, the friction that exists between two non-moving surfaces. And we can say, you know, Fs equals mus Fn, to say that the coefficient of static friction, which would be given, or you could solve for it if I gave you the other two, times the Fn. Remember that if it's on a slant, then Fn is not the weight, and we'll get to that a little bit later. Only when it's on a horizontal surface is Fn mg. But if it's on a slant, then it's going to be mg cosine theta. We'll get to that more later. You have Fk equals kinetic friction. So we have Fk equals mu k Fn. Also remember the interesting observation is that if you're looking at if you're looking at mu-s versus mu-k, that mu-s is going to be greater than mu-k for a set of materials. So if you're looking at something on a surface and you're looking at the coefficient of static friction between those two surfaces will be greater than the coefficient of kinetic friction for those same two surfaces. Remember, think about it like this, you know, in your own experience, mu-s, it's harder to get something into motion, easier to keep it into motion. We also learned about tension force. So sometimes we label that as just T, capital T, and this is tension. And we usually use that with hanging objects, but not necessarily so. And we also used Fnet, which is the sum of all the forces that are acting on an object. And remember that when you add them, that's why I always add. So, for example, I have my Fg and I have my Fn. And let's say that I have an applied force going to the right. I have a second applied force going to the left. And I have friction going that direction. So how would that look if I were just to add them all up? So I would just write Fnet equals normal force plus Fg plus Fap. And I'll label that as Fap1, Fap2 to keep them straight. Plus Fk. So I know this is a positive value. When I plug in, I know this is a negative value, and I know they cancel out, right? This is going to the right, so whatever that number is, it's going to be positive. This is going to the left. I'm going to plug that in as a negative. I'm adding the negative, which is subtraction, but I'm still keeping in mind and keeping consistent to the definition of Fnet, which is that is the sum of all the forces. And then Fk is going to the left, so I'm going to plug that in as a negative value. So really, the Fnet is going to be determined by the sum of these positive and negative values, and that's going to give me my final answer here. All right, that would be a sample of how to set it up. Let's quickly do one. I think that's all I have time for right now. Let's do one problem in which we deal with an angle. So let's say that I have a box. The box is not on an angle. We'll start simple. But let's say it's like a grocery cart, and when I push on a grocery cart, I push down on the handlebar like that. I don't walk parallel to the grocery cart because that would be kind of weird. I have my Fg, my Fn, right? And let's say that I have friction as part of that. I have to pay close attention to this force. This is my applied force. And let's say it's 50 newtons. and let's say the mass of this guy is 10 kilograms. Okay, I have to break this into components, right, because it's at an angle. So I need to do a little box around that vector, and I need to also give you what this angle is. So let's say that this angle is 25 degrees. I need to determine, so it's really, this is the Fx of the applied force, and this is really the Fy of the applied force. Now I need to determine what is causing the motion of this object, right? So is it Fy or is it Fx? And let's make it simple. We'll deal with friction later. We'll just cut that out of the problem for now. Fy is not causing this. Fx is causing it to move in this pathway. So I'm going to deal with Fx. In order to find Fx, which is the x component of my applied force, remember that cos is close. So this angle is closest to this side. So remember, this is also dealing with SOHCAHTOA. And that Fx component is dealing with the Ka of the SOHCAHTOA. So in order to find Fx, I'm going to take my applied force, that entire value, which is 50 newtons, and I'm going to do cosine of the angle. So my calculation would be 50 newtons cosine of 25 degrees, and that's going to give me my Fx value. And let me do that real quick. That gives me 45.32 newtons. So it's going in that direction. So let's say that the question is really asking to find what is the acceleration of the object. We already found what force is causing it. Remember that the acceleration happens in the direction of the net force. The net force here is going to be the x component of that applied force, where you took out friction to make it simple, but I could just give you a number and you would just subtract the friction out of the Fx component. We know the mass is 10, so remember, going back to our equation, F net equals ma. So A equals F net over m. In this case, the only force that is causing this particular motion is going to be Fx, so we can rewrite it as Fx over m. So A equals 45.32 kilograms meters per second squared, this direction, over the mass, which is 10. Kilogram and kilogram cancel. Dividing it out by 10 is just moving the decimal over 1. So it's going to be 4.532 meters per second squared to the right. And that would be a sample problem that you might see in which you have the box not on a vector, but the applied force is at an angle, and then you have to break it into x and y components.